Somewhere out there, a star could be surrounded by a machine, not a planet, not a moon. A structure built by an intelligence advanced enough to capture almost all of a star's energy for itself. Scientists call it a Dyson sphere. And the idea isn't just science fiction anymore. It's a real framework astronomers use to search for advanced alien civilizations. This is what it would take to build one. And why, if one exists, we might already be looking for it. The idea comes from physicist Freeman Dyson, who proposed it in 1960. His question was simple. As a civilization grows, its energy needs grow with it. Eventually, a planet isn't enough. So where does an advanced civilization go next? Dyson's answer was the star itself. A star radiates an enormous amount of energy in every direction, and almost all of it goes to waste, spreading out into empty space. Capture even a fraction of that output, and you'd have more power than an entire civilization could use. The version most people imagine is a solid shell, a giant ball built completely around a star. But Dyson never actually proposed that. He imagined something more like a swarm. A Dyson swarm is a massive collection of independent structures, satellites, solar collectors, habitats, all orbiting the star at different distances and angles. Together, they'd absorb a significant share of its energy without forming a single rigid object. This distinction matters because a true solid shell runs into serious problems. A rigid sphere built around a star has no stable orbit. Unlike a planet, which balances gravity with orbital motion, a shell surrounding a star from every side would be pulled unevenly by any disturbance and drift until it collided with the star itself. There's also the material problem. To build a solid shell around a star even at the distance of Earth's orbit, you would need far more mass than exists in every rocky planet, moon and asteroid in our solar system combined. Even disassembling a planet the size of Jupiter wouldn't be enough. A swarm sidesteps both problems. Instead of one giant structure, you build millions of smaller ones, solar panels, mirrors, habitats, each independently orbiting, each easier to construct and maintain. It's a far more physically realistic version of the same idea, and it's the version most scientists now take seriously. There's a third option sometimes discussed too, a Dyson bubble. Instead of relying on orbital motion, these structures would use radiation pressure from the star itself to stay in place, essentially balancing on the outward push of starlight. It's an elegant idea on paper, but it depends on materials and engineering far beyond anything we currently have. So, why would a civilization want this much energy in the first place? Scientists rank civilizations using something called the Kardashev scale, first proposed by astronomer Kardashev in 1964. It measures civilizations by how much energy they can harness. A Type 1 civilization uses all the energy available on its home planet. A Type 2 civilization uses all the energy output of its entire star. A Type 3 civilization uses the energy of its entire galaxy. Humanity, for reference, isn't even a full Type 1 yet. We use a tiny fraction of the energy Earth receives from the Sun, let alone all of it. A Dyson swarm would be one of the clearest paths to becoming a Type 2 civilization. A level of energy access that could power planetary-scale engineering, interstellar travel, or computing on a scale we can't fully imagine. So, if a civilization elsewhere built one, how would we ever find it? This is where it gets interesting, because a Dyson swarm would leave a detectable trace. A star's light doesn't just vanish when it hits solar panels. It gets absorbed, then re-emitted as heat, specifically as infrared radiation. That means a star surrounded by a partial Dyson swarm might show an unusual signature, dimmer visible light than expected, paired with excess infrared radiation. It's a specific, physical fingerprint scientists can actually search for, and they have. Studies dating back to the 1960s have scanned stars for exactly this kind of anomaly, and modern surveys continue the search today, cross-referencing infrared data from space telescopes against visible light catalogs, looking for any star that doesn't add up. One case briefly stunned the astronomy community. In 2015, astronomers using data from NASA's Kepler Space Telescope flagged a star known as KIC 8462852, later nicknamed Tabby's star after astronomer Tabitha Boyajian, who led the study. Its brightness dipped in strange, irregular patterns, unlike anything typically seen from planets or normal stellar activity. For a brief period, a partial alien megastructure was seriously proposed as one possible explanation. Follow-up observations eventually pointed to a far less exotic answer. Multiple studies found that the dimming was wavelength dependent, consistent with clouds of dust passing in front of the star rather than a solid or artificial structure. As of now, dust remains the leading explanation, but the search itself didn't stop there. Projects like Hephaestus, a modern survey looking specifically for Dyson sphere candidates, have scanned millions of stars, cross-referencing visible and infrared data at a scale simply unavailable a few decades ago. So far, no confirmed candidate has held up. Every anomaly investigated has eventually been explained by something natural. Dust, stellar activity, or measurement error, but the search matters because a Dyson sphere isn't really about the structure itself. It's a physical signature of what an advanced civilization might do with enough time and enough energy. If life elsewhere ever crossed that threshold, this may be one of the only ways we could ever detect it from light years away. We haven't found one yet, but the fact that we know exactly what to look for is remarkable in itself, which means somewhere in the data we've already collected, or in a survey running right now, the signature could already be sitting there, waiting to be noticed. Thank you for watching this video, and for more like this, subscribe to Industrial Origin.